Okay, this is Mr. Cowboy, bringing it back around as we have another nightly edition of Physical Chemistry After Dark. Still have my Glenn Levitt. Let's pick up where we left off. We want to get into reaction mechanisms. So, how are we going to do that? We're going to do first what we need to do before anything else is go into integrated rate laws. Because once we have our rate law, we want to look at it at more than one period of time. If our rate law was our tangent to the curve, our integrated rate law is the integral of that tangent. We measure the reaction rate. Not always practical to look at the reaction rate of a reaction once it's initiated. However, if we know the rate law, we can integrate this over a period of time and calculate the concentration that will change as time progresses. So we're taking, as the rate law, we have tangent to the curve. Integral, we take the area under the curve. And from there, we can measure what a given concentration is over a period of time. So, well, integrated rate law is going to be harder to approximate with a lot of complex reactions. It can accurately survey many elementary reactions. One of the main ones we're going to look at is first order reactions. They're defined by the elementary reaction where A goes to product P. The differential rate law, or rate of the reaction, is K times A, or simply the negative differential of concentration of A for changing time. Now, how do we get the integrated rate law from this? Well, with this in mind, with the K equals A over negative dA dt, we are going to separate and isolate. So we're going to get the dt to one side and all of the A components to the other side. So we divide both sides by A to get dA over A, and we're going to multiply both sides by dt to get negative K, well, negative dt, to give you negative K dt. Now we're going to integrate it from time 0 to some point, we're going to call it time t. And so that's going to integrate it from some concentration at A0 to some concentration at time A sub time t. So integrating 1 over A dA is going to give us the natural log of A. So integrated from the interval from A sub 0 to A. So ln A minus ln A sub 0 can be evaluated and to ln A over A sub 0. Integral of 1 dt with respect to t is just going to give us t. T at time 0 is 0, and then t at time t is t, so you just have negative k t. So this gives us our integrated rate law. ln A over A sub 0 equals negative kt. If we know A sub 0 and we know K and T, we can find concentration A. Now it can also be placed into a linear format of ln A equals ln A sub 0 minus KT. Or it could even be turned into a exponential format where A equals A sub 0 e raised to the power of negative KT. Either one works. The advantage of this final form here is that it will allow us to look at product concentration as a function of A, whereas product concentration is A0 minus A, so product is equal to A0 1 minus E raised to the power of negative KT. So rather than look at concentration A, we can look at concentration of P, which is rather convenient. Now, if we look at the natural log of concentration versus time, this one, this middle one, the ln was ln 0, we'll get a linear graph with the slope of that graph being negative k and the y-intercept being the natural log of ln a sub 0. So by graphing this, the time and the concentration, we can determine our k and our a0. Now, sometimes you may not always have time to do a full graph, where half-life comes along. Half-life is important to talk about in all rate laws, but especially for first-order ones. Half-life is the defined time for one half of the reactants to be consumed from a given point. At 100%, half-life is when 50% has been consumed. If I have 50 molecules left, half-life would be 50% of that 50, which would be 25 molecules remaining. So half-life amount changes depending on where we started. But the half-life time does not always have to change. So this doesn't necessarily have to correspond to the reactants at time 0, yeah. So how do we find the half-life? Well, that, because of how we're defining half-life, the concentration at half-life is defined as 1/2 of A0. So if I plug 1/2 of A sub 0 in for A, we get that this to be an ln 1/2 equals negative K T at time 1/2. If I take that negative and factor it over, then I can get ln 2 equals K at time 1/2. There's a point where I can say ln 2 over K is equal to the half-life time. Now you notice, half-life time is only dependent on constant K and the number ln 2, meaning the half-life of first-order reaction rate depends only on the constant K and will not change. It will remain constant throughout the entire reaction. So to go from 100 to 50 may take 20 seconds. But then to go from 50 to 25 is going to be another 20 seconds. To go from 25 to 12.5 will be another 20 seconds. You can see where this is going. The most common reaction that undergoes first order is radioactive decay, meaning to go from 5 million radioactive particles to 250,000, maybe a million years. But then to go from 100 particles to 50 particles, still a million years. See why that might be a problem. Radioactive decay, first order reactions, can't really do much about it to speed this up. Now, we're going to break, there's second order reactions. We can break this down into two types. Type 1 is going to be described as literally just two molecules of A breaks down into P. So the rate is K A squared. Or essentially, the rate of equals negative 1/2 dA dt. Because of the fact there's 2A. So we get that dA dt equals negative 2K A squared. But this is going to, but the fact that K is a constant and 2 is a constant number means we can essentially encapsulate that 2K into a new constant we call K effective. Because the actual K is not really that important. Finding out real K versus K effective will not change things. So you don't really have to worry about this. Type 1 is going to be different from type 2, where type 2 will involve two different reactants, and we'll discuss that in a slide or two. So separating our variables, so we divide both sides by A squared, multiply both sides by dt. we get negative dA over A squared equals K effective dt. Integrating K effective dt with respect to t is just going to be K effective t. But integrating 1 over A squared dA is going to give us, so 1 over x squared gives us negative 1 over x plus c. But c is going to be canceled out because we have an integral range. So negative 1 over x, and that cancels out with that negative already there. So we have 1 over a minus 1 over a sub 0 was K effective t. Now we more often than not switch it to the other side to have 1 over a sub 0 equals K effective t plus 1 over a sub 0. In this case, if I plot 1 over a sub 0, the inverse concentration versus time, we can get the slope as K effective and the y-intercept as 1 over a sub 0. Rather useful to do so. The half-life of this, once again, we set A is equals to 1/2 A sub 0. And we get, plugging that in, that becomes 1 over A sub 0 times 1/2, which can simplify to 2 over A sub 0. Get 2 over A sub 0 minus 1 over A sub 0 goes to 1 over A sub 0 equals K effective T 1/2. And then if we divide by K effective, we get our half-life is 1 over K effective A sub 0. Meaning the half-life of a second order reaction type 1 has a direct dependence on the concentration of A sub 0. So the half-life will be faster at high concentrations and much, much slower at low concentrations. So looking at where we're measuring our half-life will play a very big part. So it'll slow down a lot more as it gets closer to completion. Type 2, as I said, is A plus B goes to a product. Well, the differential rate law is A rate equals Ka times B. Each one is individually first order, but the overall rate law is still second order. This becomes a little bit harder because the rate is equal to negative dA over dt, but it's also equal to negative dB over dt. Now, because the rates in regards to both reactants are the same, we can say that A sub 0 minus A will also equal B sub 0 minus B. And if we then isolate the initial concentrations, B sub 0 minus A sub 0 to give equals B minus A, we can say the difference in the initial concentration as a constant delta. So like if A and B start at the exact same concentration, then delta is 0. But if A is less than B by, say, 3 moles, we can say delta is 3. We can solve and say that B is equal to A plus delta. So essentially we get plus A to the other side and say B equals A plus delta. And that way we can solve this in terms of just one variable. Meaning, if I say dA dt equals negative K A times delta plus A. Well, let's think about this. So solve this to the other side. Factor this out. Our dt is still the same, but now we have on this side A over delta time plus A. We have to do a integral by parts. Integral of A would be ln A, but integral of delta plus A would be ln would be ln delta plus A. So we got to think about that. How do we have to integrate this by parts as saying like, yeah, dx over x plus c. So we have 1 over c. The easy way to wave our fingers is negative 1 over c ln x plus c over x. How do we get that? Well, we get this through some magic integrals that a function, if that's gx plus or minus hx, we can say the integral of that function x is equal to function of gx with respect to x and hx with respect to x. Well, we can say that 1 over x plus c is a function 1 over c plus times 1 over x minus 1 over c times 1 over c plus x. 1 over c plus x. So private x squared plus cx. So that's cx. That's c squared plus cx. So to get the point where c squared. Let's make sense. Let's see. C squared plus. Oh, I see. Wait, because if I say c plus x over c equals, and then minus negative x plus c, that is going to be c over c, which is 1. So what we're doing is saying like, okay, line c plus x over c, what we're saying here is that this cancels this. So 1 over c, there's our 1 over c times 1 over x. And this x cancels here. And that gets us 1 over c times c plus x. So it makes sense. I mean, it's a little backwards math, but it makes sense as a way we can do that. Remember, c is our delta. C is our constant. C is something that when we integrate will not show up. With that in mind, we can take each individual integral and we can do that. So that becomes, the integral of that is going to be ln of x times 1 over constant delta. And this is going to be ln of c plus x times 1 over c. So all that's all well and good. So in fact, we can factor that out, factor that in. So ln c plus x ln x becomes integral of ln x plus c over x. Now factoring that from a to a sub 0 becomes ln a plus delta over a minus ln a sub naught plus delta over a naught. Hot mess. But that delta is b naught minus a naught. B naught minus a can simplify this to 1 over b naught minus a naught ln b over b naught a over a naught. So looking at the ratio of those two concentrations is equal to kT. The half-life not really applicable for this reaction. But saying if I know the concentration of A and B, initial time, they're going to be relatively the same. We can look at those. So now, also going to look at sequential first order reactions. This is where we get into some really new stuff now. Well, the last one was really new, but this is getting even newer new stuff. So we can break down many reactions into elementary steps. Very few reactions only have one step. So we can't just look at just one step. Sometimes we have to look at multiple steps. So let's look at this initial sequence react, where A decays into an intermediate prior to forming its products as a radioactive decay chain. So like A goes to I with a rate law, and I goes to K, I goes to P with its own rate constant. The rate of disappearance of A is equal to negative Ka times A. The rate of appearance of P is dP dt, Ki times I. What about the rate of I? I will be different because it is both formed and consumed. So the change in I is both dependent on the amount of A present and the speed of A, and the amount of I present and the speed of I consumption. So it's both at consumed and formed. So we have to treat it like this. So in order to measure the concentration of I, function of time, we have to start with the first assumption that A sub 0 doesn't equal 0. The initial I sub 0 must equal 0, and P sub 0 is equal to 0. That there is no products and no intermediates at initial point. And that A being a first order, concentration A is A0 E K sub A T. So what we're going to do, we're going to plug A in for our di dt that we know. We'll plug this for A and for this into this equation. We get that, well, di dt is K sub A, A0 E Ka T minus Ki I. So all those are in terms of constants except for time. That's the advantage there. We instead of A is being changing, we have that as A sub 0 and then just in form of time and only time. Then solving the linear differential for I, we're going to get that I equals Ka A naught Ki minus Ka over Ki minus Ka, or E Ka times T minus E Ki negative Ki times T. I can prove this. It's a mess, but it involves substituting di dt plus I, or a du dv dt plus v du dt plus uv, approximating v as 0, and then solving for u. Solving for v, and then determining I is equal to u times v, which needs to make certain assumptions about the constants of integration. I can do it, but I don't want to. I really don't. I have a whole page of proof to get here. But it's, well, we'll do it in a minute. We don't want to do it. But then from there, if we know A sub 0 equals A plus I plus P, and solve for P as a function of A sub 0 minus A minus I. And we know what A is. We got that. We know now what I is. It's even that uglier thing. And we can actually simplify that to be P as a function of A sub 0, 1 times a whole bunch of constants as a function of time. I will go ahead and take a side break to try to prove that. I'm going to switch share to whiteboard. Show that mathematical ugly ass proof. I'm not just a pretty face reading off a slide. But I did this. I set these up. I mathematically solve it. We say that our starting point di or dt equals k a sub 0 e negative k a t minus k I concentration I. Well, the first thing I do is I get ki to the other side. So I get di dt plus ki concentration I equals ka0 or ka0 e negative sorry, that's kaa0. So next here comes the function that if I say, this is where I say, if I say di dt plus I px plus or minus qx is equal to, that's where the u dv dt d du u dt plus uv px, all that equals qx. Q sub x. So, oh, sorry. Oh, God. No wonder I screwed that up. Equals like qx. So, say di dt plus I of px equals qx. And that's where we get our u dv dt plus v du dt plus uv px plus qx. What equals qx. So this is our qx. This is our qx. And we're saying this is our px. So we have to find what is u du dv dt. What is our v du dt, and what is uv? So the first assumption we say, if v is actually 0, if v is 0, then this simplifies to v du dt plus u ki, that whole thing equals 0. Everything that's multiplied by v is 0. dv may not be 0, but if we say v is equal to 0, then that whole thing gets to 0. So that means that the integral of du over u equals the integral of negative ki dt. So if that's ki, we divide both sides by v, both the 0 by v. We have our du equals u du dt over u kt. Get the u kt to the ki to the other side. Divide both sides by u. Divide both sides by, or multiply both sides by dt. We have this du over u is equal to negative ki dt. So that's saying ln u equals negative ki t plus a constant. Solving for u is equal then to c e negative ki t. Annotation. Okay, I want eraser. I want to just so I want to erase most of this. So we have a way that we've essentially said if v is 0, that allows us to solve for u in terms of that. U in terms of a constant ki and time, just in terms of time. Okay. Erasing. There's a faster way to erase, but without deleting that all. But it is what it is. Now, plugging that back in, we wanted it, if v is still 0, that knocks it down to what? Just u dv dt. So u c e negative ki t dv dt equals ka a sub 0 e negative ka times t. Now, getting that to the other side, and then integrating with respect to v and t. We can solve for v. So we have integrate of dv, integrate of, so we're going to say ka over a constant c, ka a 0, mind you, e to the negative ka over t, e to the negative ki t. Those can be factored together as the same way we can factor logs. So those become e to the negative ka t plus ki t dt. And we're integrating that. Integrate that goes out. It's integral by parts. So that becomes, v becomes ka a sub 0 for c as a constant c, 1 over ki minus ka e to the negative ka t plus ki t plus another constant d now. So we have v, we have u, we have v. We can plug this back in. So v doesn't necessarily equal 0, but we used v as 0 to solve for u. And part of the original thing is uv px. Well, we know uv has to be I, concentration of I. So and it also must UV must equal I. It also must equal this times this. Our U here, which is CE to the U to the negative KIT, C to the negative KIT times, so, but it also must equal what, like C over C cancels out here. KA A naught over KI minus KA e to the what, like KI e to the negative what, like KA T plus CD e to the negative KI because of all the cancellations. So we have this, we have a way to look at the I in just terms of constants. The problem is we don't know CD. Well, so C times D so we're going to say if C times D is equal to negative KA A0 KI minus KA, then we can say that I is equal to KA A0 KI KA negative KA T minus e to the K negative KI. So that's how we solve for I. That's how we got that nasty, nasty beast of an I. So as I said, not the prettiest one, but not just waving your fingers. It's there's quite a bit of math involved. Okay. So the relationship between the intermediates, Ka and Ki, can lead to some very interesting concentration profiles based on the size of Ka and Ki. So depending on how big the rate of the first step is versus the second step. If Ka is greater than Ki, we will see a significant buildup in an intermediate prior to product formation. So A goes down, I builds up, and then eventually goes back away. If A is smaller than I, then I is immediately consumed almost as soon as it's formed. So the first one is kind of an intermediate ratio of A to K, the Ka and Ki. A is consumed, I is building up, and then it's going away. This one, A is almost immediately consumed, and I is taking a long time to convert. Thus, it much longer. So this one's 2 times effect. Ka is 2 times faster, times Ka is 8 times faster. Well, this is what happens with Ka is a quarter as fast. So you see A is going down very slowly. I is building up, but very little, and then it kind of reaches a steady state and then just kind of levels off. It doesn't really get any much higher than that. As P gradually goes up. So all these are controlled by the relationships of these rates, which leads to idea of maximum intermediate concentration. Looking at those previous graphs, you'll notice there's a time when the concentration intermediate peaks and then decreases. So at this point, where the concentration of I versus time at the T max is 0. Essentially, if you took the tangent of that line, the slope of that line is 0 because it's flat, it's level. So you can solve for that because we know what I is. We've solved I. I did that incredibly long and intricate proof just to show that, yeah, we do know what I is. I know it could have waved my hands, but that's not what this video is about. This video is about showing you the math is real. I suffered through the math once. I can suffer through it again. I can make you suffer through it. As we're trying to understand this. So if we look at that, the change in I with change in time is 0. If I take the derivative of this with respect to t and set the derivative at 0, so that EKA t at t max, that gets factored out to negative Ka, because the derivative of e to the x is going to be pull x out front and then derivative of that. Or it would be x dx, x e to the x again. And so you're pulling that out. So if we know our K and our time at max, well, we can solve our time at max based on the ratios of A and I and our initial concentration. So we can separate these guys. Because these are 0. All these constants can drop out. Thank God. Thank God. So we can separate, get Ka e to negative Ka t max to one side, and Ki to e to negative Ki t max on the other side. Essentially you can divide on both sides, natural log both sides, and then solve for t max. So let's look at that real quick. So notate. So I'm not just, we're saying, okay, K A e to the negative Ka t equals Ki to the e negative Ki t. So you divide both sides by Ki, you get Ki and Ki over Ka over Ki equals e to the negative Ki t e to the negative Ka t. Take the natural log of both sides. It goes out. You have negative Ki t over Ka t. Though, actually, I think you can factor those in before you can do that. So like becomes e to the negative Ki plus Ka t max. So that simplifies to mathematically. So you take the natural log of that. You have ln Ka over Ki equals Ka minus Ki t max. And then, of course, you divide both sides by Ka over Ki, Ka minus Ki to get this. So we can know T max just in terms of the ratio between those two constants. We find what time will we get to max out our concentration of I. Once again, if A is really big with respect to K, you get a very large K, and you get a very large K, let's say K is going to start increasing. But of course, then you're dividing by a larger number. There's a difference of Ka and Ki. If Ki is bigger than Ka, like it's doing a negative number, but you're also dividing by a smaller number. So a smaller negative number. So we can figure out that time difference. But this will allow us to calculate at what time the intermediate will top out, which can also be used to find the maximum available concentration, because we have a way to calculate I with regards to temp time, find out what's the maximum concentration as well. I'll go ahead, and this is probably where I'm going to end this video. Yeah, we're going to go to end this video here, and we'll continue again in a little bit. So once again, if you like, please like and subscribe. Like seeing me suffer through calculus, come on down, watch some more. Either way, I'm out of Glenlivet. I'm going to go get some more. Have a good night.